In this video, we prove the fundamental theorems of calculus. I have labeled the two fundamental theorems of calculus using the labels used in the Larson and Edwards calculus textbook. It's Larson and Edwards. Those are the authors. It's 7th edition. And I believe the title is Calculus Early Transcendental Functions. Different textbook authors label these differently. Sometimes this is called Fundamental Theorem of Calculus Part 1, and this is called Fundamental Theorem of Calculus Part 2. That's the way I was taught it. I was taught it in that order, this one first, then this one. Larson and Edwards like to show you this one before this one. Either one is fine. Either way is fine. But when we prove these, I think it's easier to prove this second fundamental theorem of calculus first, and then use it to come up with the result for the first fundamental theorem. So let's review what those say, and then we'll prove them. Okay, so here's the first fundamental theorem of calculus according to our textbook authors. It says, if our function f is continuous on the interval from a to b, and f prime of x equals little f. So that means that capital F is an antiderivative for f. Little f on the interval from a to b. If that's true, then the integral from a to b of f of x dx, which we can interpret as a net area, it's an area bounded by the function in the x-axis, the area above the x-axis minus the area below the x-axis between the two vertical lines x equals a and x equals b. That's equal to the antiderivative evaluated at b and a and then subtracted. So you just find the antiderivative, you plug in the upper limit, you plug in the lower limit and subtract, and that turns out to give you the value of this integral, which we've been interpreting as net area. We'll find that definite integrals can represent lots of other things, as we'll talk about in calculus 2. So that's the first fundamental theorem. It tells you how you can evaluate this without taking limits of Riemann sums, and that's very nice, because limits of, even the special case of limits of Riemann sums that we were doing with our upper sums and lower sums can be pretty involved algebraically, a little bit tedious. And then we're taking the limit as the number of rectangles goes to infinity. And as we've discussed, when the number of rectangles go to infinity, that does not necessarily guarantee that the width of that subinterval, that delta x, approaches 0, unless all of those delta x's are exactly the same size. So we've been evaluating this using a limit process, but sometimes the function is actually not Riemann integrable, so that's not necessarily equal to the value of this integral. Anyway, this gives us a much, much easier way to find that value of the area under the curve. All we had to do is find the antiderivative, plug in the upper limit, plug in the lower limit, subtract, and we're done. Okay, so that's fundamental theorem part 1. The second fundamental theorem is this. It looks a little strange, but it's not too bad if you can remember what this represents. It says, if f is continuous on an open interval I containing x equals a, so it's just a little interval, x equals a is on the interior of that interval. Then for every x in I, the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. So in practice, if I'm using this, all I do is I look at my integrand and I look at my bounds over here, and if there's an x in the upper bound and a constant in the lower bound, then as long as my function is continuous on an open interval containing a, and I'm interested in this in an x value, or at an x value where the function is continuous from a to x, all of these things hold at the very beginning. all I have to do to take the derivative of this is take the integrand, replace the x or the t with an x, and I'm done. It's that simple. Now, one of the implications of this is that this function right here, like we want to think of this not as an area. Well, this is an area, that's a finite number. But we want to think of this as an area that depends on x. So this is g of x. I'm going to call it g of x for the proof. This is the integral from a to x of f of t dt. Since this function is differentiable, we know it's continuous because differentiability implies continuity. The function can't be differentiable and discontinuous. So if we're saying we can take the derivative and we get this back, that means it's differentiable. Well, if it's differentiable, that means it's continuous. So this is a continuous function. That's one implication of this second fundamental theorem. And another implication is that it's an antiderivative for f, because the derivative of this function is f, so the antiderivative of f would be that function. So we want to keep both of those in mind. Now, one thing that helps me and that will be relevant to our proof is to think about this geometrically. Now, y does not have to be a positive function, but I'll draw it as a positive function of t over here. What this represents is the area under the curve starting at x equals a, or t equals a, and going to t equals x. So we're going from there to there. That area is g of x. And when x equals a, we have the integral from a to a of f of t dt, we get 0. But as x increases from a, we go farther and farther to the right, that area is going to increase. And this tells us that it increases in a continuous way, which I think makes sense. Just a moment later, I'm going to have a little bit more area. I'm not going to suddenly jump from one amount of area to another amount of area as x changes. So we see that that's a continuous function, and it makes intuitive sense that it would be continuous. And this is saying that that function is differentiable. And when you take the derivative of this accumulating area function, so this area that's getting larger and larger and larger as x increases, turns out that the derivative of that is the original function, but evaluated at x. Like, what? It's pretty amazing, but we're going to prove that. Okay, so here's the idea behind the proof, the plan for the proof. So we're going to let g of x be that integral from a to x of f of t dt. And we're going to assume that x is an I, and it's that same I from the theorem. So our function f is continuous. We're on an open interval I. For every x and I, this is true. So we'll let g be this function, where x is in that interval I, the one that they talk about in the theorem, and x plus h is also in the interval I. Then we're going to compute g prime of x using the limit definition. That limit definition of the derivative. Remember that x plus h or that x plus delta x? That's what we'll use here. And here's part of the idea. When I evaluate g of x at g of x here and then g of x plus delta x, so there's my x plus delta x, where delta x is positive. They've got that width right there. g of x plus delta x looks like this. Its area under the curve, but it's just a little bit more. So that red area, which includes this unshaded rectangle right here, that's g of x plus delta x. So when I take g of x plus delta x and I subtract g of x, what do I get? Well, I get like a little rectangle right here. Doesn't that look like it's approximate, the area of that little rectangle is approximately equal to the function value times delta x? Well, we'll see. That's related to what we're saying here. Okay. So we're going to compute g prime, which is the derivative of this, using the limit definition. And we want to show that g prime of x is equal to f of x. So g prime, that's the derivative of this integral which is a function of x. So it's this accumulating area function. It's giving us area under the curve as x increases. We want to show that the derivative of that has to be f of x. Okay. So now let's do it. So let's let g of x equal the integral from a to x of f of t dt. And we're assuming all of the things that they assume at the beginning of the theorem. So assume f is continuous on an open interval I, containing x equals a. So this is where f of x is continuous. And x is in the interval I. That just means x is in that interval. And x plus h is also in that interval. Or maybe we should use x plus delta x. I think that's the one that we used in this class, is x plus delta x. X plus h and x plus delta x are the same thing. So f is continuous on the interval I. X is in I and x plus delta x is also in I. Then we want to compute g prime of x using the limit definition. So if the derivative exists, then g prime of x is equal to this. It's the limit as delta x approaches 0 of g of x plus delta x minus g of x. It's just the change in the function values as x goes from x to x plus delta x, divided by the change. Well, according to this right here, g of x plus delta x looks just like that. We integrate from a to x plus delta x. We're integrating f of t dt. And then we're subtracting g of x, which looks exactly the same as that right there. And we're dividing by delta x. So let's draw our picture. Here's x equals, or t equals a. Here's x. I'm going to make it pretty large. Here's x plus delta x. That area right there is g of x. This larger area that's g of x plus delta x. Now, our function f is continuous. So we can actually break this up into a couple of different pieces using our properties of definite integrals. If I want the integral from a to x plus delta x, I could call that the integral from a to x plus the integral from x to x plus delta x. So let's write that as that. Just using those properties that we talked about. And it actually makes a lot of sense visually as well. All I've done so far is I've taken this piece right here and I just replaced it with this. I'm saying the integral from here to here is the same as the integral from here to here plus the integral from there to there, which I think makes sense intuitively. Okay, so we just made a substitution. And then look, these guys reduce. And you just get this, which I think is what we could see from the picture. If I took this whole area and then I take this part away, shouldn't I get that area, which is the area between x and x plus delta x? That's what we see here. So if the derivative of g exists, it's equal to this. So I have the limit as delta x approaches 0 of the integral from x to x plus delta x of f of t dt divided by delta x. Okay. Now, if I can, I would like to let delta x approach 0. Now, as delta x approaches 0, we'd be dividing by 0. That might be a problem, but as delta x approaches 0, the denominator approaches 0, and then this upper bound or upper limit of integration also approaches x because this is going to 0. And then we have this integral approaching the limit of the integral from x to x of f of t dt. Well, if those bounds are the same, as delta x goes to 0, I've got the integral from x to x, that's going to be 0 because when we start and end at the same place, there's no area under that curve. We're saying, what's the area under f of x from x to x? Well, there's no area there. It's just a little line segment, right? So this is actually a 0 over 0 indeterminate form, which is a bit of a problem. When you have an indeterminate form, it's possible that that limit equals something. Like it could equal 5. It's possible that the limit is 0. It's possible that the limit's infinity. It could be anything. It's indeterminate. That's why we call it indeterminate. And so we've got to do something about that. But we can actually evaluate this limit using the Squeeze theorem. So we can address the indeterminate form by using the Squeeze theorem. We can squeeze this in between two functions that we are confident are approaching the exact same thing. Okay, so remember this picture, and this is f of t dt right here. Or not dt, f of t, y equals f of t. All right. So we're trying to show that this approaches a number, and our hope is it approaches f of x. That's what we're trying to show because that's what the theorem says. It says the derivative of this should be f of x. Okay. So here's the idea. Well, if we're on the interval from x to x plus delta x, and f of t is a continuous function on that interval, then we're guaranteed that this function has an absolute max and an absolute min on that interval by the extreme value theorem. We can use that to our advantage. So we'll say, since f of x or f of t is continuous on the interval from x to x plus delta x, whoops. Let's say by the extreme value theorem, we can say the following. f attains an absolute maximum on that interval, and f attains an absolute min on that interval. And let's use the same notation that we used when we were talking about upper and lower sums. So we'll let the absolute maximum value of the function on the interval be f of capital M sub I, where M is the x value on that interval where f achieves its maximum. And the absolute min, we'll call that f of little m sub I, and that little m will represent the x value on that interval where f achieves its absolute minimum. Okay, so by the extreme value theorem, f will attain an absolute max and an absolute min on the interval from x to x plus delta x. So let's sort of zoom in to get really close to x, the interval from x to x plus delta x. So maybe our function looks like this. Who knows what it looks like, right? Could look like anything. Just that's all we know is that it's continuous. So this is our function on that little interval. So we've got y equals f of t. This is y, this is the t-axis, and t is going from x to x plus delta x. Well, the area under the curve is bounded above and below by two areas. And that area under the curve is given by the integral from x to x plus delta x of f of t dt. It's bounded above by that maximum value of the function on the interval. So it looks like m sub I, that capital one, that capital M is right here. If I find the area under the curve for this rectangle, it's going to be larger than that total area under the curve y equals f of t between x and x plus delta x. I don't know why I put those little i's there. I guess I was just so used to it from our upper and lower sums. The i's aren't really necessary. So the area of that rectangle is going to be larger than the area under the curve, greater than or equal to, unless that function happens to be constant. So it's the maximum value times the width of that interval, which is delta x. And that area under the curve is also greater than this value. Well, it looks like we get the minimum value of f right here. If we make a rectangle like this, looks like the minimum actually occurs at x. So we've got that minimum value times delta x. We've got the area of that blue rectangle. So it's the minimum on the interval and then the maximum on the interval over here. Okay. Now, if I take all of this and I divide by delta x, I get that expression for g prime in the middle. So if f min is less than or equal to the integral from x to x plus delta x of f of t dt divided by delta x, and that's less than or equal to the maximum value of f on that interval. And this is almost the expression for g prime. If I take the limit of that as delta x approaches 0, that's giving me g prime. And we're actually letting delta x approach as 0 from the right because we're assuming that x plus delta x is to the right of x. Well, if I take the limit as delta x approaches 0 of all three parts, going to put that little m back in. Oops. Well, it's not 100% obvious, but this is g prime of x. And this on the left is f of x, and this on the right is f of x. And if you're saying to yourself, how do you know that that's f of x? Well, remember what's happening. Delta x is approaching 0. I guess we should say it's approaching 0 from the right because we're assuming that delta x is positive. But as we approach 0 from the right, well, that interval is getting smaller and smaller and smaller. That minimum and maximum value, well, those are going to have to get closer together because that interval is getting so small. In the limit, as delta x approaches 0, little m and big M, that's the x value where f attains its minimum and the x value where f attains its maximum, they have to be approaching x because delta x is approaching 0. And that interval is getting so small that eventually it's just going to include x. In a limiting sense, it'll just be the interval from x to x. So what we get on the left is f of x, and we get on the right is f of x. And that's because m approaches x as delta x approaches 0, and capital M approaches x as delta x approaches 0. And this is all limits from the right. We could do exactly the same argument looking at limits from the left. The only difference in all of this would be in the way we draw our picture. If delta x were to the left, it'd be over here. But we would still have that 0 over 0 indeterminate form, and we'd have the integral from x plus delta x to x instead. It'd be flipped the other way. But yeah, everything else would be exactly the same. It would be exactly the same argument. So this is showing us that the derivative exists when we're taking that derivative from the right, as delta x approaches 0 from the right. And we can show just as easily that when you take the limit as delta x approaches 0 from the left, where delta x is a negative value, that you get the same thing. So I'll just say similarly. This is what you'll see in textbooks a lot. Similarly, the limit as delta x approaches 0 from the left of the integral from delta x, or x plus delta x to x, also approaches f of x. So g prime of x is equal to f of x. And that's what we were trying to prove. Okay, so we used all of these things. We said if our function f is continuous on an open interval I, we needed that for us to be able to use the extreme value theorem. And it contains x equals a, then for every x in a, this is true. Now, even though it might not feel like we used the fact that x, we were on an open interval I containing a, we did use that. You're making lots of assumptions about the function that we were starting with being continuous near this x equals a right here. And that was all throughout the argument that we were making. So that was necessary. And then we were able to show that if this is g of x, the derivative of g of x with respect to x must be f of x. Because this guy is squeezed in between these two guys. It's that sort of area of that rectangle from the upper sum and that area of the rectangle from the lower sum. And as that delta x gets very, very, very small, this approaches f of x, this approaches f of x. So this must approach f of x by the squeeze theorem. And we had to use a squeeze theorem on the left and on the right, and we just did it on the right, and then we said it's similar on the left. Okay, so that is the proof of the second part of the Fundamental Theorem of Calculus. Other textbooks actually call this the first part. Our textbook authors call it the second Fundamental Theorem of Calculus. Now let's use that result to prove the first fundamental theorem. This one that's so useful that we use all the time. It tells us the integral from a to b of f of x dx is just the antiderivative and evaluated at the two endpoints and then the difference between those two values. Okay, so let's use what we just came up with to prove that. So we're trying to prove that this is equal to this under the conditions that f is continuous and f is an antiderivative. And remember what it means to be an antiderivative. That just means that f prime is equal to little f. Okay, well, if f is an antiderivative, it must be related to that g of x that we just found. We were able to show earlier that the derivative of this function is f of x. If the derivative of this function is f of x, the antiderivative of f, or an antiderivative of f, is this function. So since the derivative of g is equal to f, the antiderivative of f must be equal to g. That's just the definition of an antiderivative. So we know that g is one antiderivative of f. So if g is one antiderivative of f, we've got the integral from a to x of f of t dt. So let's let g be that. And we're assuming that f is continuous. Then if f is any antiderivative, it must be the function g that we started with plus a constant c. That gives us all of them. If I take any antiderivative and I add c to it, and I take the derivative of both sides, the derivative of f is going to be the derivative of g, which is little f, plus the derivative of c, which is 0. So if g is an antiderivative, then f of x equals g of x plus c is also an antiderivative. It's actually a family of antiderivatives because f prime is equal to g prime plus the derivative of 0, or derivative of c, which is 0. So f prime is equal to g prime plus 0, and g prime is f of x from the last result. Okay, well then let's just evaluate this f of b minus f of a and show that it's equal to this. Well then f of b minus f of a is, well, this. This is our function f. So I'm evaluating g at b, and then I'm adding c to it. I've got the integral from a to x of f of t dt plus c, but I'm replacing x with b, so I substitute that in, minus f evaluated at a. Well, it's going to be g evaluated at a plus c. So we have the integral from a to a of f of t dt plus c. So I'm just replacing x with a. And remember from our properties, the integral from a to a of f of t dt, provided that a is in the domain, and we're assuming that it is. We have f continuous on that interval, so it is. And that's 0. So we end up with the integral from a to b of f of t dt plus c minus c. The c's reduce, and you just have the integral from a to b of f of t dt. Now, integrating with respect to t is the same as integrating with respect to x. It's the same as integrating with respect to u or y. The letter really doesn't matter. This is called a dummy variable. So I can just switch it back to x. And that's it. So the integral, or f of b minus f of a, has to be equal to this. So if f is an antiderivative, or if g is equal to this, and f is an antiderivative, well then, yeah, if g is equal to this, g is an antiderivative. And if g is an antiderivative, then f of x equals g plus c is an antiderivative. We can prove that by just taking the derivative. Then if we evaluate this antiderivative at b and a and subtract, we get this back. That's it. All right, guys, so those are the proofs of the fundamental theorem of calculus. If that was a little bit heady, don't worry about it. You don't need to understand the proofs to be able to use these guys. When we use the fundamental theorem of calculus, we just confirm one thing: make sure f is continuous on that interval from a to b. If it's continuous, then you're good to go. You just take the antiderivative, plug in b, plug in a, and subtract, and that's going to give you area between the function and the x-axis if the function is positive like this, or it's going to give you net area. It's area between the function and the x-axis, and it's area above the x-axis minus area below the x-axis if that function happens to be negative at some point on the interval from a to b. So that's how we use this. Now remember how we use this. If we have an integral from a number to x of f of t dt, this says the derivative of that integral is just the integrand. You just replace the t with an x, and that's it. And I think this actually makes a lot of sense now, knowing what we know about the first fundamental theorem of calculus. So let's revisit this, and then we'll finish this video. So I've got the derivative with respect to x of the integral from a to x of f of t dt. Well, according to the first fundamental theorem, the derivative with respect to x of this, well, it comes from evaluating that integral. So you take the antiderivative, with respect to t, and you substitute in t equals a, and then t equals x, and subtract. So we get this. But the derivative of the antiderivative, that's just the original function. Now f of a is a number, so the derivative of that number is 0. So we can sort of put those two pieces together and see that it makes sense.